Okay, so the first half of this lecture is gonna be quite mathematical intensive. So I will let you know from the beginning that um, the calculation, which is calculus based, don't worry if you don't get all of it because I'm trying to kind of show you that there's a way to calculate stuff, but I don't expect you to, like be able to do the full calculation in the exam or something like that. All right, so that probably should, let some of you be a little bit more relaxed when following this part of the lecture. All right, but if I'm going too fast or too slow, then please let me know because sometimes the math can be quite obscure. Okay, so before we continue, let's review a little bit what we talked about last week. So last week we introduced um, the electric field, and the reason why we did that is to be able to, describe the system without having to have like the other charge, something like that. So we know from Coulomb's law that if you have two charges, then they either repel or attract each other depending on the sign of the charge. But what happens if we just have one charge? How do we describe it? Well, obviously there's going to be no force on just a single charge because we need another one. But if we use electric field, then we can describe that without the second charge, right? So last time we said that if we have a charge, which is say Q1, and this charge we say creates electric field at every point in space. Okay, every point in space means this point has electric field. This point also have electric field. How doesn't matter how far away you're gonna have electric field. It might be really weak. That's another question. But any point in space will feel kind of the existence of the charge Q1. So let's say we are interested in this point, which I will use the green color here. So point P, and point P is a distance r away from charge Q1. So this point P will have electric field. Just to be clear, let's assume that Q1 is positive, right? So at point P, there will be an electric field pointing that way. And we can write this to be E1, which is kind of like shorthand for electric field created by charge Q1. And the direction, well, we need direction because electric field is a vector, right? So we need both magnitude and direction. So the direction of E1, because Q1 is positive, it's going to point away from this line, which is the line joining the point P and the charge Q1, right? So if you pick different point, you're going to have different direction of electric field, right? So the direction of electric field depends on where you are in space. So this is not what we call uniform electric field, right? So last time we introduced the term uniform electric field. Uniform electric field means electric field is the same everywhere. Same mean same magnitude and same direction. This is not the case. So this is not uniform electric field, right? The direction is not the same everywhere. And not only that, the magnitude is also not the same, right? Because if you are closer, the electric field is stronger. If you are further away, then electric field is weaker. And we show that the magnitude of the electric field is given by K, which is the electric constant, 9 times 10 to the 9, times the charge, Q1, divided by the distance square, right? So this is the magnitude. And you can see that there's no mentioning of the second charge, right? Because we just have Q1 and Q1 is the one creating the electric field. So you don't need like Q2 or something like that to be able to describe like the system, which is really nice because sometimes this is good enough for us. And if we want to, you know the force on, the second charge, let's say you put the second charge like here, Q2, right? So what do you do then? Well, you just use force on Q2, F2, is just Q2 times the electric field at that position, right? So we use this, and then you're gonna recover the Coulomb's law, okay? So again, this is kind of like a two-step process. Like you first write down the electric field, and then you use F equal to Q times E to get the force. Like instead of jumping directly to the Coulomb force, like F equal to K Q1 Q2 divided by R squared. The end results are the same, but the way of thinking is a little bit different. And thinking about electric field is very, very useful, not just here, but also later if you get to the point where you need electric field which changes in time, like electromagnetic wave or, Faraday's law or something like that. Anyway, this is good enough for us now. So we're going to use this kind of formula to calculate one example. And the point of this example is twofold. One is to show you how it is to do this kind of calculation. And the second point is to show you how messy it is to do the calculation. And that's going to lead to the second topic for today, which is Gauss' law. And Gauss' law is, in some situation, used to calculate electric field without, messy calculation. So that's kind of like how I will go about, like talking about today's topic. Okay. All right. So what kind of question I want to think about now? So let's consider a line of charge. So you can think about wire, a piece of wire. And a piece of wire is, it's just a really, really long kind of piece of metal, right? Something like this. And it's a straight one, right? So there's no bending. And let's say that the length of this whole wire is chosen to be L. So one end to the other end gives you the distance of L. And what we're going to do is we're going to put in some charge plus big Q into this wire. Okay, so how exactly you do that? Well, that's not really relevant here. So let's say you can do that by removing a few electrons from this metallic rod, right? So that's probably the easiest way to do. But in any case, when you put the charge plus Q into this wire, which is made from metal, which is a conductor, and last time we talked about a conductor, we know a few properties. One is that the charge will distribute itself along the surface of the metallic object. So that's what we know. So at the moment that you put in plus Q into this rod, the charge will distribute throughout the rod, right? So there's going to be some plus charge everywhere. And if you count the amount of the plus charge in the whole rod, then you're going to recover plus Q. That's the idea. Okay, so because plus Q is distributed, we can assume that it's distributed evenly on this rod. Then it's probably kind of easier if we introduce what we call the charge density. So the charge density is something that relates to the question of something like this. So if you cut the rod so that the rod has the length L, right, you just take a cutter or a knife, and then you cut it like this. And because this length is small L, how much positive charge you're gonna have in this small section, right? And you can see that, well, it's kind of like, you know, elementary kind of like ratio kind of calculation. You can just say, okay, if the whole length is L, then what we call here is lambda, which I will write Q over L. This is called the linear charge density. So it's just the total charge divided by the length of the wire, right? So if you if you take a section which is the length of L from the wire, how much charge you have in this small section, let's say small q, well, it's going to be equal to the length, which is L, small l, times the charge density, which is lambda. So altogether, you're going to have small l divided by big L times q. This. Right. So this is the charge contained in this small section of the wire. So we're going to use this to proceed with our calculation. Okay. So this is kind of like the reason why I have to introduce this linear charge density, because it's a lot more convenient to deal with. Anyway, I'm gonna erase this part. Okay, so what do we do then? Well, not only that, I will move this to a different place. So I would say here that Q over L is defined to be lambda, and this is what we call linear charge density. Okay, so what to do next? Well, the goal of this calculation is to find the electric field at this point here. So what is electric field at this particular point? And this point is a distance r away from the rod, and it's at the center. Okay, you don't have to do that, but it's a little bit easier if we choose this point to be at the center. So that means I can set up a coordinate running in the x direction. So this is what I'm going to do. So I'm going to say that at this end, this is x equal to minus L over 2. And at this end, this is x equal to L over 2. Right. So here, at the center, that's going to be x equal to 0. Right. So x is the direction in the horizontal direction that tells me the position of the on the wire. All right. So we want to know the electric field at that point. So how do we do that? Well, the only thing that we know from last time is that if we have a point charge plus Q1, then the electric field is given by this magnitude. And the direction is pointing away from that charge. That's the only thing we know. And this is something different. Here we don't have point charge. We have a wire or a rod of charge. It's not point charge. So we cannot just say that the electric field here is just K times big Q divided by R squared. This is wrong. Or even if this is not wrong for some reason, there's no reason for this to be correct, because the formula we use here is for point charge, right? So we need to show that it is this or maybe not this, right? So how do we do that? Well, even though we know the electric field for point charges, it's fine because we can cut up this wire into small sections. So the idea is this. So I'm gonna remove this part. Okay, and let's remember that this distance here is r, right? But I don't want to write it now because it's gonna make the diagram a little bit crowded. Okay, so the idea is this: if I look at just a small section on the wire, like this red section, right? If I choose this section to be short enough, let's say the whole length of the wire is 1 meter, and then I choose this red one to be 1 millimeter or half a millimeter or even smaller than that. At some point, it's gonna look like a point charge. So that's the idea. So if I choose this to be small enough, then this will act like a point charge. So this one will give out electric field according to what we knew from before, right? It's positive, so it's gonna point away like this. So we can write down the magnitude because we know the distance, we know how much charge is contained in that section. So once we are done, then we just move on to a different section. The next one, like here. And then we write down also the electric field from that section. So that's gonna be a little bit further away, so the direction will be something like this. And then you do the same. You just keep on moving. Keep on adding, right? So in the end, you just have to add all the electric field from every section on the wire. And in the end, you're gonna have the total electric field, right? So you see, this is something that we do without thinking too much about it. But it's actually based on the superposition principle that we discussed last time, right? So the fact that we can cut up this rod into many sections, and each section, if they are small enough, then we can treat them as point charges. So we can just add electric field from every single charge, point charge that we have. And then we're gonna recover the total electric field. So that's what we're gonna do. Okay, and this is how we use calculus also most of the time in physics, right? Which is to cut up our object into smaller pieces and then we just add up. And adding is just integrating in calculus. Okay, so let's be a little bit more systematic and see what we're gonna do. So the first thing you do is you need to set up the variable that you want to, like integrate. And in this case, what we do is we're gonna use the x variable, which denotes like the whole length of the wire, and x runs from minus L over 2 to L over 2, right, from left to right. So we're gonna cut the wire into a small section like this. And this small section, we're gonna call it delta x. So delta indicates that this small section is very small. And x indicates that we are cutting in the x direction, so horizontally. Okay, and then we're gonna do the delta x converting to like dx when you do the integration later. So this section delta x here is the length of the wire. So if the length of this red section is delta x, how much charge do we have in this red section? Well, it's just the length times the charge density lambda here, right? So that red part actually contains the amount of charge. So I'm gonna write here contains the amount of charge, which is also small because delta x is small, right? Contains the amount of charge, I call it delta Q. And delta Q is equal to the charge density, which is Q over L. Okay, so I will write it lambda, and then I will substitute lambda Q over L later. Um, maybe I don't have to. I don't remember exactly, but I'll keep it as lambda. So I write lambda times delta x. Okay. So again, this is the charge contained in the small section. This is the density, and this is the length of the wire. Okay. So delta Q equal to lambda times delta x. Once we know how much charge we have, we can write down the electric field at this point here, right? Because it's just a point charge. If delta x is small enough, and delta x will be small enough to be considered this as a point charge, right? So a point charge, well, what's the electric field coming out? Well, it's going to be in the direction of pointing away from the charge, so it's going to be that direction. And what's the magnitude? Well, the magnitude is going to be according to this formula here. So because this electric field is coming from the charge delta Q, right? So I will also write this electric field to be delta E to indicate that this is the electric field coming from delta Q, not the total electric field. We have to add all of this up, right? So not yet the answer that we want. So it's just the electric field from this tiny section of charge here. Okay? So another thing we can do, and this is usually the case when we solve physical problems, is that there's something in the problem that simplifies our calculation, and sometimes it's so obvious, sometimes it's not. But in this case, it's a little bit obvious because you can see that for any delta x on this side of the wire, you're gonna have the same. It's kind of like a mirror image on the other side. On the other side means it's the same distance from the center, but it's in the negative direction, right? So this is why I choose the rod to be at the center, right? Because you have this kind of symmetry. So this symmetry is kind of convenient because if you look at, well, actually, let me choose a different color so that you can see better. So it's a little bit pink, right, like this. So that also can have delta x in the length, and it's gonna have electric field in this direction, right, something like this. And because of the mirror image, right, the strength of the electric field will be the same, the magnitude per se. The direction will be different because one is pointing to the left, the other one pointing to the right. But you can see that if we decompose this electric field into horizontal direction and vertical direction, and then we can cancel that out. Same thing for the red one. We do this and we do this. Okay. You can see that the horizontal component is always canceling each other out. Because it's the same position, right? You have this kind of symmetry. And this is true for any point that you choose on the wire. Let's say you choose a different section on the wire, maybe a little bit closer here. This gonna have another point on the other side, which is gonna cancel out. So you can pair up every point on the wire so that the horizontal component cancel out. Right? This is the symmetry of the problem. And because of this, when we calculate the electric field, right, let's say we go back, we don't really need to consider the horizontal component because we know that something gonna cancel out anyway, right? So in this point is suffice to just look at the vertical component of this delta E here, right? The horizontal can cancel out, so we don't need to think about it. So that means we know already without even completing the calculation that the result, which is the electric field at this point here, will point downward. And this is purely because of the symmetry of the problem. Because you have the right-hand side of the wire equal to the left-hand side, there's no reason for the total electric field to point any other direction other than pointing down, right? Because, I mean, it's symmetric. Like, how do you know like it's gonna point left or right? So, we know that the final answer is gonna be just electric field pointing down like this. So that being said, we can write the y component of this electric field to be delta E y. And this is good because we know that the electric field is going to point down. So we can kind of forget about the direction of the electric field at this point. Right? So we're going to write something like this. So delta EY, which is the y component of this electric field, right, is equal to the magnitude of delta E, which is the total electric field, not the total, like the whole electric field from that small charge, times cosine of this angle here. Okay, I hope it's clear what I'm doing at this point. Right, so this is the y component of delta E. So it's just delta E times cosine of that angle. Right? And this angle is the same as this angle, right? Because that's when you have two lines intersecting each other. So those are the same angle. And this angle we can calculate cosine this way. So this distance is r, and this distance is x, right? X is the variable that we're going to integrate in a few moments. But at this point, the distance from this section from the center is x. So using the Pythagoras theorem, this length here, the hypotenuse of this right triangle, is just square root of r squared plus x squared. Okay, so knowing this, we can write cosine to be r divided by, so let me change the color. So it's going to be r divided by square root of x squared plus r squared. Okay, from the geometry of our problem. So the next step, we can substitute the electric field delta E. Because we know the charge, right? We can use the electric field here, right? So delta E, which at this point we only care about the magnitude, is just K, the electric constant, times the charge that we have, which is delta Q, divided by r squared. Now, this r squared is not this r. R squared in the electric field formula is the distance from the charge to the point that we are trying to calculate square. So it's actually this distance square. Right. So sometimes I'm a little bit sloppy in saying like r in the formula square is the distance, but we use also r for a different reason. So just be careful about that and think about what it means. So it's going to be square root of r squared plus x squared. That's the distance, so that's square here. And then, of course, you still need to multiply by cosine, which is the same as what we have in the previous line, like this. Okay, so again, let me indicate that this here, this part here, this is the distance from the charge, the delta Q to our point. I didn't name it. This point here, right? So that's the distance. And it's distance square, right? So we need to put a square in there. So altogether, at this point, we can write delta EY equal to K times dq, but we know that dq is just lambda times delta x. So lambda times delta x. Actually, I want to put delta x right at the end. So I'm going to write delta x later. So it's lambda times k. And remind yourself that you need to put delta x at the end. Because I have r here. And then at the denominator, I have x squared plus r squared to the 3/2 power. Okay, make sure you understand why this is 3/2. It's 1/2 here, and it's 1/2 square here, so that's 1. So 1 plus 1/2 is 3/2. So it's 3/2 power of 3/2 here, and then times delta x like this. Okay, so that's the electric field in the y direction, vertical direction, for this section of the wire, that tiny section of the wire. And the next step is just to integrate this, because we just need to sum contribution from every part of the wire. But before we do that, it might be beneficial to identify like which part of this equation or this expression is a constant, which part is not. Well, the variable that we're going to integrate is x. So obviously x is not a constant. That's going to be the variable that we're going to integrate. Let's check the rest. Well, k is a constant. Lambda is a constant because it's the total charge divided by the total length. That's not going to change. What about small r here? In this problem, small r is the distance from the wire to this point, which is also fixed. Okay, so that's not going to change. So it looks like we are fine. The only thing that's going to change, or the only thing that is variable, is x, which I have already highlighted with blue here. Okay, and EY is also going to be the variable that you're going to integrate on the left hand side. So that's fine. All right, so the rest is math. So let's do that. So I'm going to copy this to be delta EY equal to K lambda R divided by R squared plus X squared to the 3/2 power, and then times delta X. Okay, and we're gonna do a thing which, I mean, most of mathematicians will not like, which is I'm gonna say that, okay, if delta X is small enough, then we're gonna say delta X is just dx. And delta EY is gonna be dEY. And this d here is the dy by dx that you have seen. That's the derivative of the function with respect to x. Okay, so I mean, rigorously you need to do the limit or whatever. We're not gonna spend too much time doing that because we know that eventually it's gonna work. So we're gonna do the transformation right away. So we're gonna replace delta with d so that we can integrate it. So we're gonna do something like this. And then write dx here. Okay, so once we change delta to d, then we can integrate it, which is kind of a silly thing that I have to do this, but somehow this is what we are used to. So just maybe don't complain and then just proceed. So we're gonna integrate. So the act of integration is to sum all contribution in the system, right? So again, what we are doing here, the delta EY, oh actually I skipped the space up here. So the delta EY here, that's the electric field only from this tiny section, but that's just one tiny section of the whole wire, right? If you want the whole wire, then you just need to add everything up, right? So that's the part that we're gonna do next. All right, so to integrate is to sum all the contribution. So we just need to put the integral sign. So integrate dEy is gonna be equal to integrate k lambda r divided by r square plus x square to the 3/2 power, and then dx like this. So the next thing is to put in the limit of integration. For the left hand side, it's easy because if you don't add anything to the system, it's going to be 0. So it's going to be 0 to EY. Right. So again, the mathematician will not really like this because I'm not supposed to use the limit of integration to be the same as the integrating variable. But again, I don't really care about that. So what about dx? Well, just look at your system, the wire here, and see the range of x that you need to integrate. It's going to run from minus L over 2 to L over 2. Right? So that's going to be our limit of integration. So it's going to be from x equal to minus L over 2 to x equal to L over 2. Right? So our task here is just to evaluate this integral and we'll be done. So let's do that. The left hand side is easy because it's just EY. And the right hand side, you can take out all the constant because it doesn't change the integral. So it's going to be k lambda r, and there's nothing else we can do. So we need to put the integral sign here. 1 over r square plus x square to the 3/2 power, and then dx. Okay, so that's what we have here. And at this point, well, the thing is that if you know how to do this integral, then you just do it. If you don't, then what do? Well, you just ask someone who knows how to do it, and then that people might look up the table integration and then tell you the result. But anyway, I don't really care because this is not a math class. This is a physics class. So as long as you know how to get the integral using computer or using whatever, it's fine. Okay, so that means if I look up the table of integration, you're gonna find, well, this is quite common integral. It's not that difficult to do, but it's also not that easy. So I'm gonna write down the result here. So integrating this, you're gonna get x over r square 1 over square root of x square plus r square. That's the result here. Okay, so doing this, then we can just use the result and then substitute the limit of integration. So it's equal to k lambda r. After the integral, you use this bracket just to make it clear. So it's x over r square 1 over r square plus x square. It's square root, right? So this is 1/2. And then you need to put the limit from x minus L over 2 to x equal to L over 2 like this. Okay, and then the next step is you just substitute in the limit of integration. So you can even cancel one factor of r here. That's what I'm gonna do here. And then here you're gonna get L over 2 divided by r square plus x square. So it becomes L square over 4, 1/2. And then minus, and then x equal to minus L over 2 here. And then r square plus L square over 4, 1/2. Right. So you can see that the minus sign here cancel out to give the plus sign. So altogether you have k lambda over r. And then you add these two together, so you get L over r square plus L square over 4, 1/2. So that's the answer. And what you can do is, like, if you don't like this lambda, because that's something that we kind of, made up, right? It's not the variable that's given by the problem. So you can substitute lambda equal to L, equal to Q over L. So lambda is Q over L. That's how we define it. So it make it a little bit nicer. So you have K, Q, and then L. This L here will cancel with this L. So we're gonna have K, Q divided by R times R square plus L square over 4, 1/2, like this. So this is the answer. So after this long calculation, it's probably good to check whether we did something wrong. Or that's kind of true, no matter it's a long calculation or short calculation, right? So, well, let's check if the the formula have the correct unit. So if you remember, the whole thing here is the electric field in the y direction, so EY. Electric field is KQ divided by R square, right? So K is here, Q is here. And it's something that is distance square in the denominator. So we have R distance. And we have R square plus L square, so that's good. And then 1/2 factor, so that becomes just a distance. So the unit works out fine. Okay, so this actually give the correct unit, so at least we know that it's probably okay. Anyway, what's interesting is this. So this is the electric field from a piece of wire which is this long, right? So sometimes the wire is really, really long, almost infinitely long wire. So we're gonna put the limit. So if, sorry, one different color. So if R, not R, I want the distance, the length. If L goes to infinity, which is infinitely long wire, then the electric field is equal to EY. This formula with R going to infinity, right? So I'm gonna write limit of R going to infinity of KQ divided by R times R square plus L square over 4 to the 1/2 power. not R, there's no R here, it's L, right? So L goes to infinity like this. So when L goes to infinity like this, so what happened here? The thing is that when L is really, really long, then I can forget about this factor R squared here, right? So I don't know whether it's obvious to you. I'm gonna write it this way. So just this factor here, this part here, because that's the only factor that contains L, right? So when you take the limit of L goes to infinity, this factor here, L squared over 4, 1/2, can be approximated as just L squared over 4 to the 1/2. And for some reason, I always write one kind of like in a slant way. So, right. So let's say R is like 1 meter, and then L is like like 1 kilometer or something like that. So this is very small compared to this. So you can just forget about small r. In this term, it's nothing to do with the r in front. That's still something that you need to keep. Okay. So it's gonna be this, which is, well, you don't need approximation. So this is equal to just L over 2. Right. So this blue term here, when you take the limit of L goes to infinity, it's gonna be just L over 2. Right. So in the end, Ey, after taking this limit, it's gonna be just 2kq divided by r times L. So because the wire is infinitely long, the amount of charge you have is also a lot, right? Because if you think about the wire which has a fixed charge density, right? The longer the wire, the like the more charge you're gonna have, right? So in the end, it probably doesn't really make sense to keep X and L here, because if you say the charge density is fixed, so it's probably better to replace this Q over L to be the lambda variable that we defined earlier. So to summarize, we can say that for an infinite wire that has charge density lambda, then the electric field in the y direction is given by 2k lambda divided by r. Right. So this is from this. So maybe I'll write one step so that it's not too confusing. So it's kq divided by r times L, but then we rewrite this part here, q over r, to be lambda, right? So you can say that this is equal to 2k lambda divided by r. Okay, so that means if you have a really, really long wire, let's say this long wire, and we know that the charge density is lambda, right? So that's charge per unit length. Then at the distance r from the wire, then the electric field will point away from the wire, because again, this is due to the symmetry. So don't forget that it's infinitely long, right? So you cannot tell left from right, essentially. But the electric field at this point here has the strength of k lambda divided by r. Okay, so again, the point of this whole exercise is to first show you how to calculate this. And by this, I don't just mean this particular configuration, right? If you have a different configuration, for example, if you have a sphere, well, that's not a sphere. If you have a sphere of charge plus Q, and this is the conductor, right? And you know from last time that the charge will, the previous slide, I'm gonna show you before the break, okay? But right now I just want to talk about this point first. So if you have a sphere, a conducting sphere, and then you have a charge, and the charge will distribute over the surface, right? So it's gonna be plus Q everywhere. And if you want to find out what's the electric field at this point, we need to do the same thing, meaning that you need to cut out the sphere into a small section, and then you need to add electric field from this tiny section all together, and then you need to integrate it, right? So this principle here applies to any shape of, object that contains charge that you want, right? Whether it's easy to integrate or easy to calculate or not, that's a different question. But in principle, this is how you do it, right? And for this particular case, when the wire is infinitely long, we have this expression, right? But in order to get this, you need to integrate and then take the limit. So after the break, I'm gonna talk about what we call the Gauss law, and we're gonna obtain this solution without having to go through, like the whole exercise in mathematics. Okay, so it's probably a good time to take a break. It's a little bit early, but that's probably better than start talking about the new thing. Okay, so I will start again in 10 minutes. And is this the page that you want to look at? Or where? Previous slide. Is this page? Okay. All right. So I'll leave it like this, and then I'll see you in 10 minutes.